We're going to talk today about C++20, and we're going to talk about not some of the big features that other people have already talked about today, but some of the smaller features. But before we do that, let's have a look at the release schedule for C++20. So, as you know, C++ has a release cycle of 3 years, and the C++ Standard Committee meets 3 times a year, so that means we have 9 meetings in order to finalize the new standard. I've given actually a version of this talk before. The first time I did it was in June in St. Petersburg at the user group. And that was just after the Kona meeting, which was the meeting where we're supposed to be feature complete. So at the time I was thinking, C++20 is feature complete now, it's a good time to talk about it. But then I gave the talk a second time at CPPCon in September, and that was after the Cologne meeting. And then stuff had changed. So I had to tweak some slides. Some features that I had talked about the first time were removed. Other things subtly changed. So I gave a talk again with some changes. So now, just last week, we had another meeting of the committee in Belfast. And again, some stuff has changed. So now we're here. And again, I had to tweak my slides a bit. And I think today, this is going to be the ultimate version of this talk, because now I think we have 1 meeting left in Prague in February next year, where we're just going to fix a few last-minute bugs, but I can't see how anything can change, really. So this is now, I think, we really know what C++ is going to look like, C++20. But what are we going to talk about, actually? So the C++ standard, about a third of it is the core language rules, like the first third, and about 2/3 of it is the standard library. So today, we're not going to talk about the library at all. We're just going to talk about language features, okay? So what language features do we have in C++20? So if you look at that, we have a few big ones. We have, obviously, concepts, which you might have heard about. We have modules. We don't have contracts. Actually, contracts were removed, so we don't have contracts. I'm not going to talk about that now. You can maybe chat to me later at the bar. I'm happy to share some stories about what happened to contracts. But we do have coroutines, and we do have the spaceship operator, or consistent comparison. And those are like the big features. And we're not going to talk about any of those. We're going to talk about the rest, okay? And I tried to kind of group that into a few kind of chapters, so to say. So we're going to talk about, first, initialization, very important. We're going to talk about structured bindings. We're going to talk about lambdas, templates, const expert, compile time computing, and then at the end, we're going to have a few miscellaneous items. Some of those things will be kind of new features. Other things will be additions or improvements on existing features, like structured bindings. We already have them in C++17, but they're better. Again, lambdas, we have had them since C++11, but now they're better, and so on and so forth. So let's start with initialization. So actually, last year, at this very stage, I gave a talk about initialization in C++. So this is very great, because now we can take off exactly where we stopped last time. Let's talk about initialization in C++20. Let's talk about aggregate types, right? You know what aggregate types are. So aggregate types, you can initialize them with aggregate initialization, right? Curly braces. So that's been there since forever. But now we have a new way in C++20 to initialize aggregates, which are called designated initializers. Right? So now, instead of just initializing the elements of the aggregate from first to last, you can just kind of type which element you want to initialize. So you can say, well, A should be 3, and C should be 7, and you don't mention B, so B will be 0 initialized. Okay? And that's actually a feature that has been in C since C99. So really what this is, it's a C compatibility feature, except that in C++ it works slightly different from C. So this is only for aggregate types, obviously. It works almost like in C99, except one difference is that in C you can switch the order around, so you can initialize C and then A in this initializer list. In C++ you can't do that. You can't change the order. So you can leave elements out in the middle or in the beginning and the end, but you can't basically change the order. You can't go C first and then A, because in C++, unlike C, initialization order matters, right? So if you have like a struct, you initialize the members kind of in declaration order, and then you destroy them in the reverse order, so the order matters. The other difference to see is that you can't nest these initializers. You can't do .c.e, but what you can do is .c brace.e. And then, unlike C, you can't mix designated initializers with regular initializers, but why would you do that? That's really confusing anyway, right? And then you can't do it with arrays, because again, like, yeah, you don't really need that. But yeah, we have designated initializers that makes it, I think, nice to initialize the elements of an aggregate in an explicit way. Let's talk a bit more about aggregates. So actually, the other thing we did in C++20 is we changed the definition of what an aggregate is. So in C++17, an aggregate class is a class with no user-provided or explicit constructors. In C++20, an aggregate is a type with no user-declared constructors. So that was done to fix a particular loophole, which was kind of really weird in C++17. So now in C++20, you can no longer have an aggregate with declared constructors. So in C++17, you could have, for example, a struct like this where you declare a constructor, but you delete it, so you don't define it. So in C++17, that's an aggregate type. Because you deleted the default constructor, you can't initialize it like that, right? That's an error. It's going to say, default constructor is deleted. But in C++17, if you just add curly curly, that turns the default initialization to aggregate initialization, then it's fine. And that was really confusing, and many people weren't even aware of this, because typically if you do this, you don't want, if you write a class like that, you do this because you don't want the user to initialize one of those things, but then they still can. And that's probably not what you intended. So almost everywhere where this was the case, this was probably not what the author of the class intended. So we changed the rules. So now in C++20, this is going to be a compiler error. So this is a breaking change, sorry, but I think if you're bitten by this, then probably the class was not written the way you intended in the first place. So talking about aggregate initialization, in C++17, there are a few other problems with aggregate initialization. So one problem is that aggregate initialization with these curly braces, it doesn't work with macros, okay? So if you have something like that where you have parens, that works inside a macro like assert. Assert is a macro. But if you have curlies, that doesn't work, right? That just breaks the preprocessor. You get like a nasty compile error. And that's because, so the preprocessor has arguments separated by commas, and there's a special rule in the preprocessor that knows about nested parens, but there is no special rule for curlies, or actually angry brackets either. So if the compiler sees the second line, it thinks that the comma is actually separating the first preprocessor macro argument from the next preprocessor macro argument. And then everything just breaks, right? Because that's just not valid syntax. So, but we don't want to touch the preprocessor. So how do we make this work? There's actually another problem with aggregate initialization in C++17, which is even more annoying, which is it doesn't really work with templates and generic programming. Specifically, you can't use it for, you can't perfect forward the constructor arguments of an aggregate. So that means things like make unique or in place or other functions that rely on perfect forwarding, they just don't work with aggregates. You just can't make them work with aggregates. So but in C++20, we fixed all of these problems. So in C++20, there's yet another way to do aggregate initialization. So now you can initialize aggregates with parens, right? So this code will work in C++20. So you can now initialize an aggregate with parens, and that also works with arrays, because arrays are also aggregates. So now you can initialize arrays with parens, which is the same syntax as if you were calling a constructor. And this is really nice, I think. So this solves this problem because you can use the parens in order to implement in place and make unique and all these functions for aggregates. So they will just work. But also, you know how in C++11 they introduced uniform initialization, and it didn't quite work as planned, I would say. So, but I think now we really have, so to say, uniform initialization 2.0, because what this does is, if you can use parens for aggregate initialization, it means basically you can use either parens or curlies all the time, and they mostly do exactly the same thing, except the curlies, if you have a class that has a std initializer list constructor, the curlies will call that, the parens won't. So now you can use the curlies if you want to say, hey, I really want to call a std initializer constructor, right? For example, for a vector or something like that. And then the other thing that curlies do is they don't allow narrowing conversions. So again, then you can say, okay, if you want to forbid narrowing conversions, you can use curlies. For everything else, both of them do the same thing, so you can stick to parens, and then you don't run into problems with perfect forwarding and templates and macros and all these things. Okay, so that's really nice. So aggregates got a lot better. There's more stuff that has to do with initialization. So here's the problem. Let's say we have a class, and that's actually a thing. I was bitten by that in practice, in production code, and I'm sure many of you have. Let's imagine we have a class, a color, okay, and it has a constructor that takes, RGB values, whatever. And then somewhere else, maybe in another file, you have a namespace with some static colors, right? So you have like a constant color, red and maybe green and yellow, whatever. So you define a bunch of constants in a namespace, which will then be basically static variables, right? They have static storage duration. And that's a thing specifically like this in the framework, for example, I worked on for a while, and in many other code bases, I'm sure. So this static red color, how is this initialized? So this is a static variable essentially, right? So this is what we call dynamic initialization, right? So this is going to be initialized at runtime. Because it's a static object, it's going to be initialized before main runs, right? So before main runs, there is this runtime thing that first initializes all the static objects and then runs main. Is there maybe a problem with that? What's the problem here? What happens if you have another object, which is maybe also static, which depends on this color red? Yes. So you run into what we call the initialization order fiasco, right? It's not guaranteed in which order these objects are initialized. And if they rely on each other, then probably you're going to run into UB because something is not initialized yet and your program is going to crash. And that's the thing. So that's really unfortunate. How do you get out of this? Well, I mean, right now, we have a pretty straightforward way out of this. You can say, okay, well, color could maybe get a const_expr constructor. So now it becomes a literal type. It becomes a type that you can construct at compile time. And then you can say, well, my constant static color red object is going to be const_expr as well. And now you get what we call constant initialization, which happens at compile time. Okay, so now color red is going to be initialized at compile time. So now you're good. Now you're safe. Right? So now you can do this stuff, and you're not going to run into any problems. So this is what you should do. But there is a case where this doesn't quite work either. So this works really well if that stuff is const, right? Because const_expr also implies const. But what if you don't want this to be const? What if it's not color constant red, but some background color, which you want to initialize but might change later, right? So it's like a static object which might change later. So what happens now? Okay, so well, it kind of depends on what get background color is, right? So it could be const initialization at compile time. It could be dynamic initialization at runtime. You don't really know. It depends. If get background color itself is a const_expr function, then it's going to be at compile time. If it's not a const_expr function, then it's going to be at runtime. It's going to compile, but then you're going to run into this problem again that the order is undefined and maybe your program's going to crash. So you want to prevent that from happening, right? So in C++20, we got a new keyword which lets you do that. It's called const_init, and you can slap it in front of this object. And that basically says this has to be initialized at compile time. This has to be const initialized. So now what happens is that if getBackgroundColor is a const_expr function and can run at compile time, this will succeed, and you get constant initialization. Everything's fine. It's not going to crash. It's going to be at compile time. It's going to be fine. If getBackgroundColor is not const_expr, then it's not going to compile. Then you get a hard compiler error saying, well, this has to be initialized at const initialized at compile time, but this isn't initialized at compile time, so you're going to get an error. So it's going to turn a runtime error into a compile error, which is a good thing. So this only compiles if if you have constant initialization. So this is very useful to get around this initialization order fiasco thing. One more thing with initializers. So do you know how in C++17 we have if with initializer and switch with initializer? Well, in C++20 we also get for with initializer, which is not only consistent, but also actually is really useful and solves other problems. So let's imagine we have a function that returns a database, okay, by value. Now, let's say you want to then take the users or whatever other range from this database and then loop over all these users and do something in a range-based for loop, okay? Is there maybe a problem here? Well, it depends, right? So if a database returns something by value, then that's a temporary object, right? If then gets users, returns a reference to something inside that temporary object, what happens then? Well, if you first start running this for loop, you're going to create the temporary, you're going to return this reference to the users, but then the temporary is going to go away. Then you're going to have a dangling reference, right? And that, depending on how this is implemented, but that might be undefined behavior, okay? Because you're going to have a dangling reference to a database that was a temporary and doesn't exist anymore if you actually enter the loop. So in C++17, obviously, you can solve this by initializing the database first. Okay, now it's a thing. Now it's not a temporary object, but like a proper object that's alive when you enter the loop. But then it's defined outside, so it kind of enters the outer scope. You pollute the outer scope. So you want to maybe, put curlies around it to limit the scope, but then it's very verbose. So in C++20, you can just, initialize it right there. So for initializer, semicolon, and then the range-based loop. So I think that's really nice. All right. So that's what we have about initialization. Let's talk about structured bindings. Structured bindings were introduced in C++17. I really like that feature. It lets you write stuff like this, right? If you have a tuple or a pair or an array or a struct, which has some public members, it lets you initialize an object of that type. But instead of giving a name to the object, you give it a name to the parts of the object, right? With the syntax. And that, then the code after that becomes a lot shorter because you don't have to repeat widget.a, widget.b everywhere. So it's really useful. The problem with that is because A and B, they're just names for the parts of the widget. They're not really objects, right? So C++17 doesn't let you do many things that you can normally do with objects. Like, for example, you can't make them static. You can't make them thread local. In C++20, they behave a lot more like proper objects. So you can do these things in 20. There's another thing that you cannot do in 17. In 17, you cannot capture a structure binding in a lambda, right? So that's going to tell you, well, that's an error. You can't capture A because A is not a variable, which is true. It's not a variable, right? It's a name for a part of a variable. But, you would expect this to work, right? This is clearly useful. So in C++20, this works. So this is, I think, really nice. So you can do this. One question remains. What should happen exactly, right? So because, remember, the widget is the actual object here, right? So if you capture this A, should it capture, so by copy, right? So it captures it by value, so it copies something. Question, should it copy the whole object, or should it copy just the variable, the member variable? Which thing should it copy? It's not obvious. There was some discussion on the committee about which way around it should be. What do you think should happen here? Sorry? The member. Yes. So, and that's exactly what's happening. This is what I think most people would expect. It's going to copy A, the member, and not the whole object. So it actually has, meaningful semantics. All right. So you can capture structured bindings in lambdas now. That's great. So now we're talking about lambdas anyway. So let's keep talking about lambdas. Lambdas in C++20 are awesome. So first thing, we have this feature which is probably useful if you write a lot of templated kind of generic code. So now in C++20, you can capture a pack expansion in a lambda. So that's really useful. That lets you basically move a variable parameter pack into a lambda, right? That's useful if you write lots of kind of templated code. But the really exciting thing is that in 20, lambdas are allowed in unevaluated contexts, like decal type, for example. And if they don't capture anything, so if they don't have any internal state, then actually they are default constructible and they're assignable as well. And that's really, really cool. So basically what that means is, well, if you can use them in unevaluated context, it means that you can use them in decal type. So you can say, okay, decal type lambda expression is going to be the type of that lambda expression. Okay, that's maybe not useful in itself like this, but it allows you to do a lot of stuff. Like, for example, now you can declare a lambda like that, right? Because it's also default constructible, because that doesn't capture anything. You can say decal type of that lambda and then declare the lambda there. And you might say, well, that's still not very useful because I can do this today with auto f equals, the lambda expression, right? But this allows you to do something that you could never do before, which is you can have a lambda member in a class. So now you can put that in a class, and you can have a member of lambda type. And that's something that 20 now lets you do, and that's really, really cool, because now that works really nicely with everything that's templated on some type which is callable, or invocable, like function pointer, lambda, struct with an operator, paren. So anything that, for example, takes a callback and then it's templated on the type of that callback, you can just give it a lambda in the type. And you can store a member of that type without having to pass it in. You can just construct it there as a member, and it knows how to construct that lambda. And that comes up again and again, and that's really, really useful. For example, if you have a unique pointer, right? Unique pointer is one of those things where it takes a deleter, right? Which is essentially some kind of callback, can be any type of function-like object. So in C++20, you can, for example, if you have a unique pointer with your own custom deleter and it's lambda, now you can say, well, I'm going to do my own template alias with a unique pointer with my deleter, and you just give it the lambda expression right there in the type and just define that type. And then you can create these unique pointers, and then you don't have to specify that lambda anymore. You don't have to pass an instance of that lambda into the constructor. It's just part of the type now. It's going to just construct them in there, and that's fine. Or with sets, for example. Sets have this comparison function, right? Same thing. If you have your own, if you want to write the comparison function as a lambda, right there, you can do it in a type, okay? So that's really cool. Here's another thing about lambdas. So since C++14, we have these generic lambdas, right? So where one of the parameters is you say auto, and then that's essentially going to be a template, right? So we can do this with lambdas since C++14, but we couldn't do this with regular functions, which is kind of weird. So now in 20, you can do this with regular functions, and that's really cool. That's kind of a consequence of concepts. So we're not going to talk about concepts because it's a big feature, but basically concepts lets you write a function concept auto x for the parameter. And then if you just omit the concept and just write auto x, basically that's an unconstrained parameter. And that's going to turn the function into a template. But I think this kind of creates a nice consistency finally between generic lambdas and generic functions or function templates. So you can write it like that. So now you have auto return type and auto parameter. And that's a really nice, neat, kind of concise syntax how to write a generic function. But what if you want to name the template parameter in there? So for a templated function, you have the choice, right? You can write it like this with this new syntax, or you can write the traditional syntax where you can write template type name t and then function template, and there you have the t. So the problem with lambdas in C++17, coming back to lambdas, is that you can't name this t, right? So you can write a generic lambda that takes an auto parameter, but you don't have access to this t. Maybe you want to do something with the t, right? Maybe it takes a vector of t's, but then you want to initialize a t in the body of that function. But lambdas in C++17, you can't do that because you don't have a way of naming the template parameter. So in 20, you can do that now. So you can, after the square brace that says now a lambda starts, you can put the angle brackets with the type name t with the template parameters. And if you do that, that's optional, obviously. But if you do that, then you have the t. You have given it a name, and then you can use it inside the lambda. So again, that creates that makes lambdas and functions kind of a bit more similar. So I think the only thing that's really missing now is to have this shorthand syntax for freestanding functions as well, where instead of writing type name t, you can write void f type name t. So you can't do that in 20, but maybe I'm going to write a proposal for that. Let's see. Maybe you're going to get it in 23. And then lambdas and functions, the syntax will be really completely consistent. All right. So lambdas, functions. What else do we have? So we're talking about templates, right? So let's keep talking about templates. And now this is something that literally just happened last week at the committee meeting in Belfast, which I'm really excited about. So before we had in C++ 20 in the draft, we had a new way of using non-type template parameters, which was so that you can use more types as non-type template parameters. But it was defined in kind of a little bit of a weird way by, it kind of fell out of the spaceship operator stuff, where you would say, okay, it was defined in terms of like a defaulted, you can now default the operator equals, and then the compiler will generate like equality operator itself, and then, so the proposal was kind of saying, so if you can do that, then the compiler kind of compared two instances of that type at compile time, and then those were the types that you could use as non-type template parameters. But then so one of the national body comments was that it doesn't quite work. But now what we got last week is actually people were saying, yeah, it doesn't work. And then they went off and completely redesigned this. And now it's really, really awesome. So this is like, brand fresh stuff. So first of all, okay, what's a non-type template parameter? So this has been in C++ since forever. Non-type template parameter, right? So you have something here which is not a type but a value, and that's part of the type, and you can use that inside. But in C++ 17 and before, those things could really only be integers, right? Or types that we can treat as integers, like pointers or enums, right? So in C++ 20, it's going to get a lot better. So first news is, as of last week, you can use floating point types as non-type template parameters, which was not possible before. So that's really, really useful. So now you can template on a float value or a double value. And that's really cool. Like, for example, I work in audio processing, where we have lots of things where we have filter coefficients, or we have like lookup tables at compile time that we want to like create at compile time and things like that. And this is all floating point math that you want to do at compile time, so you don't have to do it at runtime. So for this kind of stuff, this is super useful because you can basically program the floating point types at compile time. You could do this before with const exp functions, but now you can actually have floating point values that are part of the type, okay? But it gets better than that. So now we're saying, okay, so we can use integers and now also floats and doubles as non-type template parameters. Let's call these types that we can use as non-type template parameters, let's call them structured types, okay? And now we're saying any type, class type, that has only public members, which are themselves structured types, that whole thing is also a structured type. And you can use that also as a non-type template parameter. So now we can go ahead and have a user-defined class with multiple members in it. And you can use that as a non-type template parameter. Okay, so now it's really cool. So now you can wrap several values in a class. And you can template on that value, right? So now you don't even have to create this member anymore. It's just becoming a part of the type. Okay? And then you can create them like that. So yeah, and that opens up very, very interesting, I think, programming techniques, which I'm really looking forward to using. All right, templates. What else? In C++ 17, we got a feature called class template argument deduction, or CTAD. I've done a bunch of talks on CTAD as well. CTAD works nice in C++ 17, but it wasn't quite complete. So what is CTAD? CTAD means if you have a template, you can omit the template arguments, right? And it's going to deduce the template arguments from the initializer. So if you have a vector of ints, and you initialize it with an initializer list of ints, you don't have to write the int. It's going to see, well, you initialize it with ints, so I'm going to do template argument deduction on the class, and I'm going to deduce vector of int. So it saves you typing, basically. Same with a tuple or a pair or a std array. So now you don't have to specify all the tuple types, and you don't even have to do auto tuple equals make tuple. That was kind of a hack, right? So you use a freestanding function like make pair or make tuple because that can do template argument deduction. But actually, you just want to do that directly on the type of the variable that you're initializing, and then CTAD lets you do that, right? So, but that's C++ 17 stuff, right? Here's another example. Like you don't have to write out the type of the mutex. But it wasn't quite complete. So in C++ 20, you now also get CTAD for aggregates and for alias templates. And these were things that didn't work before that people were saying, this is really confusing. Why does this not work? In C++ 20, it does work. So let me give you an example with aggregates. So let's say you have something like this, which is, if you instantiate it, this is going to be an aggregate. And then you initialize it with, 2 values. So in C++ 17, you had to basically always teach it the way that you would say an aggregate always needs a deduction guide, an explicit deduction guide. Because CTAD works on constructors and deduction guides, so that's what it uses to deduce the type. But then an aggregate doesn't have any constructors, so there's nothing to use to deduce the type. So you always had to write this deduction guide yourself, right? Otherwise, it wouldn't work. And this deduction guide really is annoying. It doesn't really add any information because you're saying, well, if you see an aggregate of T and U, then deduce an aggregate of T and U. So this is kind of boilerplate. So in C++ 20, this is now, the compiler is now generating it for you. If it sees something that is an aggregate, it's going to automatically generate this deduction guide for you. Here's an example that's even more cool. So this is a pattern which is really interesting. So you can basically inherit from a bunch of types, which are like variadic template arguments. And then in C++ 17, that's an aggregate, right? So the elements of an aggregate are the base classes and then the data members. So here we only have base classes, but those are the elements of the aggregate. So that's an aggregate. If you then in C++ 17 write this deduction guide, what you can then do is you can give it, for example, a bunch of lambdas, and then it's going to inherit from these 3 lambdas, right? And it's going to deduce the types of the lambdas for you. You can't spell them out, but you don't have to, because they're going to be deduced. So you just write overloaded with no template arguments. It's going to deduce the base types for you. It's going to inherit from these 3 lambdas. It's going to give you an overload set of these functions. That's really cool. And then, for example, if you call it with a string, it's going to call the string version, the third one. It's going to print the hello world in quotes. That works really well with std visit, for example. This is really cool. It's like a way to create an overload set from a bunch of lambdas. But you still had to write this deduction guide, which is, again, weird. So in C++ 20, you don't have to do that because it's an aggregate that is just generated for you, and this code just works like that. And so CTAD works with aggregates now, but it also works with alias templates. That's another thing that's really annoying in C++ 17, where if you have an alias template, like PMR vector, for example, so you can write vector v equals 1 to 3, and it's going to deduce vector int. But you cannot write in C++ 17 PMR vector v equals 1 to 3, because it's not a template, it's a template alias. So in C++ 17, you have to write PMR vector int. In C++ 20, CTAD works with alias templates. So that code also just works the way you expect. All right. So templates are cool. What is also cool is meta-programming in general. So let's talk about const_expr. So const_expr is really exciting because in C++ 20, we added a lot of stuff to what you can do in a const_expr function. So const_expr functions, started out relatively modest in C++ 11, where in C++ 11, they could only have a single return statement with some expression, and that's the only thing that a const_expr function could have. In C++ 14, they got better. In C++ 17, they got better. In C++ 20, they are now really, really powerful. So now in C++ 20, inside a const_expr function, you can have a try block. You can't actually throw an exception at compile time, but you can have the code in there. You can have an assembly block. We're going to see later why this is really useful. as long as it's not actually evaluated at compile time, because that doesn't make any sense, you can have it in there. You can use unions at compile time. So now the compiler knows like what the active member of the union is at compile time if you initialize these things at compile time. You can have virtual functions. You can use inheritance, have virtual functions, and call them. And whenever, like all the types are like const expr types, and the compiler can see at compile time what the actual type of that thing is, it's just going to work. So you then also get dynamic cast and type ID, and you can also now do new and delete at compile time. And that is really exciting because that opens the door to implementing things like const expr vector and const expr string, which we're also going to have in C++20. And it lets you do a lot of stuff at compile time. And that kind of sets the stage for even more cool stuff, which hopefully we're going to get in 23, like reflection, right? So you need things like that for that. So this is like a really big topic. So I could talk for the whole hour just about this stuff. But I'm not actually really the expert here, right? So I haven't worked on that stuff. So what I want to do instead is I want to refer you to two other talks by these people, by David, his C++ Now keynote from this year, and Louis Dion, his talk from CPPCon last year, where they talk in a lot more detail about exactly these features and what you can do with them. And it's really, really cool, really, really powerful. So I really recommend you check out those talks. Because these people have worked for a long time on this, and I mean other people as well, but it's a really exciting area. So I'm going to talk just a little bit about what else you can do at compile time. So imagine you have a function which computes the square of a number, okay? It just multiplies it with itself. So, okay, maybe not very interesting, but you can do this at compile time, okay? So you can make this const expr. This was possible since C++ 11. Const expr is this weird kind of thing where, actually when const expr came out in C++ 11, it took me a while to actually even understand that. That was really confusing for me, where it doesn't actually say this is a compile time function. It says it might be running at compile time. It might also be running at runtime, right? That's what const expr is. So if you give it like a 3, which is like a compile time constant, it's going to run this function at compile time. If you're going to give it a runtime variable x, it's going to generate executable code and run this thing at runtime. And so it can do both of these things. But sometimes you don't want the runtime thing. You want to say, no, I really just want to use this at compile time. This should be just at compile time. Because, for example, the only thing you want to use this for is to use the result as a nontype template parameter, for example, right? So in C++20, there's a new keyword for that called const_eval. We actually have quite a few new keywords which start with the letter CO. So I counted. In C++17, we have 5 of them. In C++20, we have 11, okay? So this is another one of these keywords that start with CO, const_eval. And const_eval says, this has to be evaluated at compile time, right? This is a function that can only run at compile time. So this is never going to cause any runtime code to be generated. This is a pure kind of compile time thing. There was quite some discussion around how to spell that. The initial proposal was to say const expr exclamation mark, like really const expr, but then the committee didn't like the didn't like the exclamation mark, so there was some discussion around that, and we settled on, hey, why don't we introduce a new keyword? So that's const_eval. So what's going to do now is if you call it at compile time, it's going to run the thing at compile time. If you try to call it at runtime, you're going to get a compiler error, okay? All right, so that's really cool, but there's still one thing missing here. So we have this thing where sometimes you might want to run something at compile time, sometimes you might to run it at runtime. But sometimes the thing you want to run at runtime is different. Like, for example, let's imagine if you want to compute the square of a number at runtime, you would have some kind of magic and intrinsic, like __ magic fast square. And your CPU has like a special instruction to compute the square like in a really cool, really fast way, which is not just I times I. So obviously for square, that's not a thing. But for example, for inverse square root, it is, right? There is a special instruction for that, and for other things as well. So now there's a bit of a problem, right? So we can obviously compute the square at compile time. At runtime, you want to compute it using this magic intrinsic because that's really fast. But now we can't make this const expr, right? Because that's a pure runtime thing. That's like a runtime thing. So we have this function, which can run only at runtime. And if we have the const expr version, we can't put the magic intrinsic in there, right? So the const expr one will run at compile time or at runtime, but at runtime it's going to use the slow, boring version. So what you really want to do in a lot of these things, for example, if you have math functions, then you want to make them const expr. But what you really want to do is you want to kind of overload on whether the function is const expr or not, right? And that comes up a lot when you have like any kind of math function, you want to const exprify it, then you really want to do this. You want to say like, okay, at compile time, I'm going to use this code, which is going to compile as a const expr function. At runtime, you want to do some special magic, which you have hand optimized or whatever. And you want to be able to overload on this, whether you're compile time or not property. And so C++ 20 now has a tool for that, and it's called status constant evaluated. And that's a magic library function which returns true if you're running at compile time, and returns false if you run at runtime. And that allows you to do this thing where you have basically these two branches, okay? So if you're running at compile time, it's going to do the thing that will compile at compile time and do the right thing at compile time. The other branch is the runtime branch, and that's where you put the magic fast intrinsic that only runs at runtime. And this is really cool because this is actually evaluated at compile time as well, right? So if the compiler sees if status constant evaluated, and it knows it's running at compile time because, for example, it's evaluating something that is then used as a non-type template parameter or whatever, or like the size of a std array, which is like a compile time thing. And it's going to evaluate this function like during a context like this. It knows at compile time, okay, I'm at compile time, so it's going to take the first branch, everything is going to work. And then once it finished, generating all the compile time stuff, now it knows everything from now on will be runtime. So now it's going to know, okay, now I can actually optimize away the status constant evaluated stuff because from now on it's always going to be false. So actually this whole branch stuff actually goes away, and this never creates any runtime overhead. Because by the time you hit the runtime and your program actually runs, this branch is gone. And now you only have code generation for the magic fast square branch, which is, again, what you want. So you have this kind of branching on whether you're doing compile time stuff or not, and also you don't have any overhead at runtime. So this is really the best of both worlds. There's only one maybe slightly confusing thing about this, which usually comes up when I show this slide. Oh yeah, why is it standard library? That's not what I meant, but this is a good question. So there was actually last week kind of a discussion around should it be like a keyword instead, should it be like a language thing, but then yeah, it's like there are different ways you can do this, and basically there was no consensus exactly how to do this. But this, like I think GCC already has this, so we already know that this works. The question usually is, well, but why is this a runtime if? Because this is a compile time. You decide at compile time whether you're at compile time. So some people, like when they see this, they think, oh, shouldn't it be a if const expr? Right? But actually, no. This cannot be if const expr. Think about what it would mean if that would be an if const expr. So if const expr is the thing that's only evaluated at compile time, okay? So if you would write if const expr is constant evaluated, that would always be true, right? So this whole function just wouldn't make any sense. So this is why don't use if const expr with this. Use it exactly like that with the runtime if. And this is exactly kind of the pattern in which this function should be used, and this is how it will work. All right. So we're almost at the end. We just have a few more kind of miscellaneous items which didn't really fit into any of the other categories. First one is something that annoyed me pretty much since I figured out how templates work. It's like code like this. Is this going to compile? So you have like some algorithm that you call, and you want to template this on container type, and then you return an iterator of that container type. Is this valid C++ code? Yes, thank you, Fabian. So this is not going to compile. The compiler is going to say, no, you have to write type name container iterator. because it's a dependent type. So whenever you have a dependent type and a template, you need to write type name. And yeah, so sometimes it makes sense if you have like A::B, it could be either a variable or a type, right? So sometimes you genuinely need to disambiguate it. But in this context, and many other contexts like this, the compiler knows it's a type because it's a function with a trailing return type, right? So of course the thing after the arrow needs to be a type. It can't be anything else than a type. So the compiler already knows it's a type. It's telling you, it's not telling you like, is this a type or a variable? It's telling you, yeah, it's a type, but you have to write type name. But it already knows it's a type, so that's kind of redundant. So in C++20, all these cases got removed, so you don't have to actually write type name anymore. So whenever you have a context where the compiler knows it's a type, you don't have to write type name anymore. So this code in C++20 will compile. That's good. That, I think, removes quite a lot of unnecessary, oh no, compiler error, like need to fix this kind of situations. We have a bunch of new attributes in C++20. So we have likely and unlikely, which you can use to give the branch predictor a hint, which branch is more likely, which might lead to more optimal code being generated. Actually, I learned recently you need to be a bit careful with this. So sometimes if you use this, the code that is getting generated is actually worse than the code that would be otherwise generated. So you always need to look at the actual code gen. We also have this one, no unique address, which is really cool. So what this does is, do you know how, empty base class optimization, where if you inherit from a class that is just an empty struct, it's not going to use up any memory. It didn't work with members. If you have a member, which is like an empty struct, it would still like consume at least 1 byte of memory because like all the members need to have unique addresses. And then, depending on what the alignment requirement is of the thing below it, you could waste like several bytes on an empty member. So if you give it this no unique address attribute, then the compiler is just going to not use any memory for that. So that's kind of, you can optimize the size of your structs, which is really cool. We have, so we had no discard before, but now you can put it on constructors, which is also really useful. And then the other thing is, if you mark a function with no discard, you can give it a kind of comment where if you don't use the return value, the user is going to get a compiler error with that string. So you can, if you're as a library author, you can say, well, this is why you this is what you did wrong. So this is better compiler messages, error messages. Another one is using enum. So you know how in C++11 we got enum class, which is obviously a lot better than the classical enum because it's safer and so on. But one thing that is different in enum class is that you always need to type out the type name, right? So if you have an enum class, this kind of color, vacuum blue, with an enum you can just write red. With an enum class you have to write type name : : and sometimes these type names are really, really long, like here, and sometimes you need to write a lot of them, and sometimes people say, well, this stuff is really annoying, so what they end up doing is they end up using the old enum instead of the new enum class, just because they don't want to write this boilerplate, but that's not wrong because... but now in C++20, you can write, well, using enum type name, and then you don't have to repeat that. So that saves you a lot of typing, but also lets you use, the enum class, which is, the safer enum. And that's really cool. And that also works not just at function scope, like here, but also at class scope. Like if you have a class and you use like enum variables everywhere in the class, you can use the using enum at class scope, and that's also going to work. So think of it as, it's pretty much like using namespace, right? If you think of an enum as a namespace for a bunch of integer constants, then you can use like using namespace and then just use the names of those integer constants. And that's exactly the same. This is how it works. This is what this is. And then the last one is about Unicode. Everyone loves Unicode. Emojis, right? So we already had this thing before where you had UTF-8 literals, like U8 quote. But what does that do? So you could store it in a const char star. But so this compiles, right? Because char star can alias any other type, so this compiles. But what is that going to do? So if the system encoding of the system that you're running this code on happens to be UTF-8, then this happens to do the right thing. But if your system encoding is not UTF-8, like for example on Windows, it will definitely not be UTF-8, then this is just not going to do anything meaningful. So you're going to have a const char star which points to a bunch of garbage. So in C++20 now, this is a compiler error, which is good. Again, breaking change, sorry for that, but like this didn't make sense before, so it should really be a compiler error. And what we have now in C++20 is a new fundamental type, which is char8_t, which is the right type for this. And that's now going to store, that's now a pointer to a proper UTF-8 string. And you can actually rely on that actually, behaving like a UTF-8 string. And there's a bunch of library stuff around it as well. So now you have U8 string, std U8 string, and std U8 string view as well. And they're all doing the right thing. The only thing we don't have yet is I/O streams for char8t. So you don't actually yet have a way of getting any UTF-8 into your program or out of your program. But as long as you're inside your program, everything works, which I think is a big step forward. All right. So so that's what I have here. So again, this is the release schedule. So we are now one meeting away from finalizing C++20. So this is going to be the last C++20 meeting, which is going to be in Prague in February. And we are pretty much done. We just have like a few last-minute bugs to fix, and then we're going to have a new standard next year. And then hopefully the compiler vendors will be quick implementing all these things. They have been very quick with this stuff lately, so I'm very optimistic that next year, sometime next year, we're all going to be able to use C++20 and use all these small things in C++20. So that's all I have. Thank you. And I believe we have time for questions. We have like 7 minutes left.
Or should I wait? Oh, okay. Let's go. Okay, so thanks for the talk, Timur. That was very informative, and I wanted to just discuss a small nitpick of mine with structured bindings. First time a coworker of mine introduced me to Vin, I say like, yes, this is magical. It works just the way I expected. But then I realized I couldn't ignore any of the parameters. Like I can put underscore, which is going to create like an underscore variable, but then I get like an unused variable warning. So do we have any solution for that or anything in the future?
Not in C++20, but this is being looked at. So I actually wrote a proposal at some point where I was saying maybe we should be able to like omit things at the end and they're going to be ignored, and then that didn't get through because people said, well, that's not enough. You want to be able to ignore things in the middle as well. And then there was kind of a discussion about what the syntax of that should be, and it didn't really go anywhere. And then we have another much bigger, language feature coming up, which is pattern matching. Maybe this could be solved with that. So I think there will be stuff happening in the space for C++23, but there's no concrete solution for that yet. But we're aware of the problem.
Thank you.
Hey, thanks for your talk. When you mentioned that now you can mix curly braces and parens, my first thought was most vexing parse. What about that?
So if you have most vexing parse, then obviously you need to use curlies if it doesn't compile with parens. But actually, often there are better ways. Like for example, if you have like A paren, B paren, and that doesn't compile because of some vexing parse stuff, you can use always auto instead of saying A, B, you can write auto B equals type. So you can just like write the auto at the left and the type on the right.
So that means we still got most vexing parse, and
So
Then that's another point where I can't use them interchangeably, so parents and braces.
So yeah, so you obviously still have the vexing pass problem. If you write it that way, then it will still be parsed as a function declaration if it can be parsed as a function declaration. Thanks. So yeah, that didn't change.
Hi, so I wanted to ask what happened with floats and in templates and equals in floats, what changed? Like for a long time there was no floats as a class template.
Yes.
Because I think about comparison, if I'm not wrong, so what changed?
Well, so yeah, traditionally the committee always said no when someone said, you want to use floats as non-type template parameters because, so what the compiler has to do if it instantiates templates is it needs to be able to compare types, right? If you have a specialization, the compiler needs to figure out whether that type is that specialization or maybe not, and then it needs to be able to compare types. You can't really compare floats. So, but now that the committee had to think anyway about allowing a lot more stuff to be used as non-type template parameters, that kind of fell out as, well, we can just say, we have this already, like for example, atomic float already doesn't do the float equals thing. Like if you have an atomic float, you do compare exchange, it's going to do a bitwise comparison of the float instead of the floating point comparison. So, for templates, we're now doing this as well, where you need to be careful, right? So you can't rely on, two floating point numbers being equal. So you have to be careful, but like now that we're allowing a lot more types as non-type template parameters, it kind of makes sense to allow them too, and you kind of need to watch out for this, but it's useful.
Hi, thanks for the talk. I must say that what you did is an impressive feat, as in to collect everything that's in the everything else sections, especially since I found that all the features you've presented are valuable. And I was just curious, did you leave out some less valuable, less important features? I mean, in the standard as it is before the last meeting?
Yeah, so this is not everything, obviously. There's loads more, but I only had an hour here, right? So I think it was kind of, we had a bunch of these meetings, and I was actually, there at all of these meetings. So I followed this process, and I kind of kept keeping notes. So I was like, yeah, this is like a good opportunity to kind of reflect on everything that happened. But yeah, there's so much stuff, and it's impossible to follow everything. So I just kept notes of what I found interesting myself, and some of the stuff I worked on myself as well. I think these are most of the kind of, how do I put this? I think this is a majority of the miscellaneous category features, but I definitely left out some stuff, yeah. It's too much.
Do you mean that this is based on your experience of the meetings as opposed to the draft of the standard?
New experience. So at the end of the meeting, everything that has been voted into the draft goes into the draft document. So
yeah,
I'm not sure what your question is.
Yeah, my question was the contents that you've shown today is based on your experience of the meeting as opposed to you reading the draft of the standard. Is that right?
Yeah, it's like a result of being there and stuff is being discussed and also reading the reports afterwards. It's not diffing the new standard and the old standard.
Yeah.
No, this is
cool. Yeah, that was great. Thank you so much.
Oops. All right. I don't see any more questions. So, yeah, again, thank you very much for coming to my talk and being here. And I'll be here for the rest of the week so we can chat. Thank you.